Welcome to this explainer. Today we're tackling a really bizarre paradox in modern AI. We're spending absolute millions, just massive amounts of GPU compute to build these incredibly brilliant, lightning-fast agents. But when these super smart systems actually need to talk to each other across a network, they use these incredibly bloated, frankly old-school methods. If you're building or running multi-agent systems right now, you've probably felt this. You felt the friction of weird latency spikes, those unexpected bandwidth limits, and lingering security gaps, maybe without even realizing exactly where that friction is coming from.
I mean, think about the sheer absurdity of how we handle this right now. We've optimized literally everything else, right? The models, the hardware, the prompt engineering. But when Agent A needs to share a complex insight with Agent B, we force them to use slow, inefficient text strings. We are effectively throttling supercomputers by making them text each other. It's this massive structural bottleneck that, honestly, most developers just accept as the cost of doing business in the cloud. But it really doesn't have to be this way.
So here's our roadmap for today. We're going to cover the token boundary, meeting Chorus fabric, using math instead of words, security woven into math, proof in the benchmarks, and finally, the future of agents.
All right, let's jump right into section 1, the token boundary problem.
So this right here is the actual root of the problem. We call it the token boundary. Think about how an AI model natively understands the world. It doesn't think in English. It uses embeddings. And embeddings are essentially the AI's native brainwaves, just lists of floating point numbers or mathematical vectors that capture deep semantic meaning. But right now, to move that state from an agent on one server over to an agent on another server, we force that native math into human-readable words. We're talking JSON payloads wrapped in HTTP. It's kind of like forcing an AI to translate its deepest thoughts into a completely foreign language just to cross a wire, only to have the receiving AI translate it all the way back into math. It's just a totally unnecessary and incredibly costly translation.
To put this into perspective, imagine two brilliant mathematicians working in adjacent labs. They've just solved this incredibly complex problem as a matrix on a whiteboard. Now, both of them speak matrix natively, right? They understand the math instantly just by looking at it. But under our current network paradigms, to share their work, they aren't allowed to just show each other the whiteboard. No. Instead, they're forced to describe every single number in that matrix using long-form English prose. Physically walk over to a fax machine, fax that huge description over to the other lab, and wait for the second mathematician to redraw the entire matrix from the text. I mean, it sounds completely ridiculous, right? But that is exactly what our AI models are doing right now. Multi-agent systems are losing time, space, and precision by effectively faxing prose instead of just sharing the math directly.
So, in practical terms, every single development team out there is paying this painful four-step translation tax on every interaction. First, the raw float 32 math is serialized into bulky JSON text. Boom. That instantly blows up the file size, and it can even mess with your mathematical precision. Second, it's sent over HTTP, which drags along all that heavy overhead of headers and text transfer. Third, the receiving agent has to parse that JSON, and that is incredibly heavy, CPU-burning work, often requiring you to run the data back through an embedding model. And fourth, the whole thing relies entirely on connection-level authentication, like standard TLS. That means if a middle box, like a router or a proxy server along the way, gets compromised, the actual AI signal inside the payload is completely exposed and vulnerable to tampering. So literally every single network hop is costing your team money, milliseconds, and security.
Which brings us to section 2. Meet Chorus fabric.
I love this quote from Insight IT, the creators behind this new protocol. They say, AI agents should talk in math, not tokens. Enter Chorus fabric. This is a completely free open-source MIT licensed protocol. And listen, that open-source part is absolutely vital because it means there's zero vendor lock-in. You can literally start building on it right now. Chorus is essentially designed as a highly efficient postal system built purely for streaming agent math. It stops the translation tax entirely. By defining exactly what the bytes mean for AI signals right down at the protocol level, agents bypass that whole text phase and literally just stream their mathematical thoughts directly to one another.
Let's dive deeper in section 3, math instead of words.
So instead of those heavy JSON strings we talked about, Chorus moves raw float 32 tensors directly as binary data over gRPC. Now, if you aren't familiar with it, gRPC is this incredibly high-performance, open-source universal framework developed by Google, and it connects services ridiculously fast. Chorus leverages this to just yank out the serialization step completely. And I really want to emphasize this point. It doesn't compress the text. It bypasses text entirely. The raw float 32 stays raw float 32 from the exact precise moment it leaves the source agent until the millisecond it arrives at the target. Zero translation.
And the architecture itself is highly versatile. It actually features 3 distinct communication modes, and we got to break these down because they are genuinely fascinating. First, you've got direct mode. That's your standard point-to-point pipeline handoff. Simple, fast, gets the job done. But then you have mode A, which is called orthogonal isolation. To explain this simply, think of it like lanes on a massive digital highway, where the mathematical properties physically prevent the cars from crashing into each other. Multiple agents can share a single network pipe, but because they're mapped geometrically, they experience near-zero crosstalk. We are talking 0.0000006% interference. It basically acts like wavelength division multiplexing, but for AI thoughts. And then there's mode B, holographic superposition. Imagine a massive choir where every individual person is singing a different note, but together, the acoustics perfectly combine into one single beautiful chord. That's exactly what mode B does. Multiple agents broadcast their individual signals, and the protocol mathematically combines them into one collective vector right on the fly. It is absolute magic for coordinating swarm behaviors.
Moving right along to Section 4, Security Woven into Math.
Now, obviously, sending raw data over a network sounds pretty risky, unless you protect it correctly, right? And this brings us to a massive zero-trust victory for Chorus. Unlike our standard setups where TLS simply secures the pipe, meaning if a bad actor breaks into the pipe, they get all the water inside, Chorus fundamentally rethinks this whole concept. It weaves encryption and per-message authentication directly into the vector payload itself. So you are securing the specific water, not just the pipe. It's true defense in depth. It secures the actual AI signal so that even if the network socket is totally 100% compromised, your agent's thoughts remain completely unreadable and untampered with.
So how does it actually achieve this level of payload security without just destroying performance? Well, it's because the encryption is quite literally a matrix multiply. It uses a tensor multiplication cipher with orthogonal QR decomposition keys. Now, hey, without getting bogged down in all the textbook math here, orthogonal QR decomposition basically just means creating mathematical lock and key pairs that a GPU can process natively and instantly. Because it's all just matrix multiplication, this encryption runs right alongside the neural networks on the exact same GPU doing the inference. You completely avoid that massive bottleneck of having to route traffic away to separate cryptographic microservices. It's incredibly elegant.
All right, Section 5, Proof in the benchmarks. You know, theory is great, but real-world data is where we actually feel the impact. Just look at these figures from a live Azure deployment running from Virginia all the way to Frankfurt. Guys, that's an entire ocean away. For a standard 128-dimensional float 32 vector, CHORS clocked a latency of just 179 milliseconds. That is 1.8 times faster than standard HTTP REST. And look closely at that cipher overhead row, 0 measurable milliseconds. Achieving 0 measurable delay for military-grade encryption across an Atlantic cable, that is an incredible engineering feat, and it's made possible entirely because the math runs natively on the GPU.
And the bandwidth savings are equally striking, and trust me, this connects directly to your cloud bill. By bypassing the token boundary entirely, CHORS stays near the physical floor of 512 bytes for this type of vector. It comes in at 548 bytes total once you add protocol framing. Compare that to the 2,440 bytes for JSON over HTTP. That makes CHORS roughly 4.45 times smaller. If you're running a high-volume multi-agent system, shrinking your payload size by over 4 times translates directly into massive cuts to your AWS or Azure egress costs. So it's not just faster, it is vastly cheaper to run.
And what about that built-in payload security we talked about? Well, in a live test of 7,766 consecutive transatlantic transmissions, the rolling SHA-256 neural watermark achieved a 100% verification rate. Basically, this relies on something called cosine similarity. You can think of that as the unique mathematical shape or the fingerprint of the signal. If a bad actor intercepts the payload and changes even one single number, that mathematical shape warps entirely. The system instantly detects the mismatch and just rejects the compromised message. Perfect security validation. Which brings us to our final section, Section 6, the future of agents.
What this patent-pending architecture actually means for your multi-agent stack moving forward is massive. Listen, if you're an AI platform engineer, the one awake at 2 a.m. trying to figure out why your crew AI swarm is lagging or why your LangGraph pipeline is racking up huge cloud bills, this is built specifically for you.
This open-source fabric drops right in to replace your inter-agent transport layer. It is a perfect fit for multi-tenant clouds that require true zero-knowledge relays, or honestly, anyone pulling their hair out over painful cross-region latency and those steep text translation costs. As we step back and look at the big picture here, we really have to recognize a simple truth. The agent revolution will not run on fax.json forever. When our most intelligent machines already think, reason, and process the entire world in hyperdimensional vectors, the network between them should absolutely speak vector too. It needs to be coherent, secure, and it shouldn't lose fidelity by translating through human language. So the only real question left is, are your agents speaking math yet?